Step into the Coliseum. The gates are closing, the clock is ticking, and you're standing face to face with the Cambridge IGCSE Physics Paper 4. And let me tell you, in this arena, only the prepared survive. Welcome to this explainer where we are going to tackle radioactivity with absolute gladiator-level strategy to maximize your exam marks. I'm your host, and today we're not just reading a textbook. No way. We're decoding the exact strategies, the hidden traps, and the precise frameworks you need to conquer your syllabus code 0625, 0651, 0652, 5054, or 9702 exams. Now, think about a real Cambridge Physics past paper question for a second. Imagine you're sitting in that exam hall. Next to you, metaphorically speaking, are two typical students. First, there's Alex. Alex is a walking encyclopedia. When a question asks for a simple state and explain, Alex completely overloads the paper with raw physics facts, dumping everything they know without any actual analysis. Just a wall of text. The result? Red marks everywhere. Next to Alex is Sam. Sam rushes. Sam sees a question, completely ignores the command word requirements, writes half an answer and moves on. The result? More red marks. Today, we're going to fix both of their mistakes and yours by transforming that red ink into glorious green check marks. Let's dive in. Here's our battle plan. We'll start in the radiation arena. Confront alpha, beta, and gamma radiation. Tackle decay equations and half-life calculations, and then wrap it all up with safety, real-world uses, and decoding exam command words. All right, Section 1, the radiation arena. Let's get right into the invisible forces around us. You might actually be surprised to know that you're surrounded by background radiation at this very moment. Literally right now. The examiners absolutely love to test your awareness of the environment before diving into the complex math stuff. When Cambridge asks you to describe what is meant by the term background radiation, this is exactly where students like Alex and Sam start losing marks immediately. Alex will write a whole chaotic paragraph about nuclear reactors melting down, while Sam will just scribble radiation in the air. Neither of those gets full marks, right? We need precision. Background radiation refers to the constant low levels of radiation we are exposed to all the time, from both natural and artificial sources. We have to clearly distinguish between radioactive substances, the physical materials themselves, and the radiation, which is the energy or particles they actually give out. Think of it like this. If a radioactive substance gets inside us, we are contaminated. If the radiation simply hits our bodies from the outside, we are irradiated. You've got to remember that distinction, because examiners frequently set trap questions swapping the words contamination and irradiation. Now, what's really fascinating here is the actual breakdown of these sources. The data clearly shows that 85% of background radiation is entirely natural, with only 15% coming from artificial sources like medical X-rays. Breaking it down further, 42% comes from radon gas in the air, 18% from buildings and soil, 14% from cosmic rays from space, and 11% from food and drink. And get this, only 1% comes from the nuclear industry. So how do you answer a question based on this data? You use the PEL framework: point, evidence, explanation, link. This is the secret weapon top students use. Your point: most background radiation is natural. Your evidence: 85% comes from sources like radon gas. Your explanation: radon is naturally emitted from rocks in the ground. Your link: therefore, artificial sources like the nuclear industry contribute a negligible 1%. Look at how beautifully structured that is. It practically forces the examiner to give you full marks. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_GCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's keep building this momentum. Understanding these forces isn't just about passing tests, though. Historically, a lack of knowledge had severe tragic consequences, as seen with the radium girls who were unknowingly irradiated. These women painted luminous radioactive paint onto watch faces back in the day. Because radium is chemically similar to calcium, the body gets confused. It literally replaced the calcium in their bones with radium, weakening them and causing fatal cancers. They were being contaminated internally because they would lick their paintbrushes to get a fine point. If an exam asks you to describe the hazards of radioactive contamination, use this historical context to ground your knowledge. Contamination means the source is inside or on the body, continuously irradiating the cells from within, which is incredibly dangerous. Moving on to Section 2, alpha, beta, and gamma. Let's meet the three heavy hitters of radiation. This is where your physics knowledge must be absolute ironclad. The emissions from unstable nuclei happen in a totally random process. You cannot predict exactly when a specific nucleus will decay, nor the direction the emission will travel. But you absolutely must know the characteristics of what is being emitted. Notice how an alpha particle is heavy and positively charged, a beta particle is a fast negative electron, and a gamma ray is neutral electromagnetic radiation. I want you to imagine our student Alex's answer to the prompt: compare alpha and beta particles. Alex writes, alpha is helium and beta is an electron, and alpha is bigger and beta is smaller. Red marks, it's too vague. Let's rewrite that using our Peel structure and transform it into a green checkmark answer using our physics success blueprint. Point: alpha and beta particles differ significantly in their physical composition and charge. Evidence: an alpha particle consists of 2 protons and 2 neutrons, giving it a +2 charge, whereas a beta particle is a single high-speed electron emitted from the nucleus with a -1 charge. Explanation: because of this mass difference, massive alpha particles travel much slower than the lighter, faster beta particles. Link: this massive size difference directly dictates their behavior in electric fields and solid materials. Boom! Full marks. Their physical makeup directly dictates their penetrating power. Heavy alpha is easily stopped by a thin sheet of paper, while neutral gamma requires thick lead to be absorbed. Think of alpha particles as the bowling balls of the subatomic world. They are massive, they smash into air molecules, causing massive amounts of ionization, which means they lose their energy very quickly. They only travel about 5 centimeters in air. Beta particles are more like speeding bullets. They can travel a few meters in air but are stopped by a few millimeters of aluminum. Gamma rays, being electromagnetic radiation with no mass, basically subatomic ghosts, are the least ionizing but the most penetrating. They travel at the speed of light and need several centimeters of dense lead or meters of concrete to be stopped. If a question asks why is alpha the most ionizing but least penetrating, your immediate rewrite should link its large positive charge and heavy mass to its rapid energy transfer through collisions. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's hit Section 3, Radioactive Decay Equations. Time to balance things out. Moving to a prime area for scoring calculation marks, let's look at how unstable atoms actually transform. This right here is where Cambridge separates the good students from the truly great ones. You simply cannot afford to lose marks on decay equations. They are purely logical puzzles. Radioactive decay happens when an unstable parent nucleus emits radiation to become a more stable daughter nucleus of a completely different element. You might be wondering, why are some nuclei unstable in the first place? Usually, it's because the nucleus is just too heavy, or it has too many neutrons compared to protons. It's unbalanced. So to reach a more stable, comfortable energy state, it throws off mass or energy in the form of these radioactive emissions. You can use a foolproof 3-step checklist to perfectly balance any radioactive decay equation in your exam. Step 1. Identify if it is alpha or beta. If it's alpha, you're dealing with a helium nucleus, so write down 4 at the top for the mass and 2 at the bottom for the protons. If it's beta, an electron is being emitted, so write down 0 at the top and -1 at the bottom. Step 2, conserve the top numbers, the nucleon number. The total number before the arrow absolutely must equal the total number after the arrow. Step 3, conserve the bottom numbers, the proton number. Again, the left side must equal the right side. Honestly, it is just basic algebra, but under the intense pressure of an exam hall, students rush it. Don't be a Sam. Take a breath and balance the numbers. All right, let's jump into Challenge 1 of our interactive workshop, a data scan. You have a 60-second visual countdown timer running in your head right now. In this alpha decay example, observe exactly how the nucleon number decreases by 4 and the proton number by 2 to ensure both sides of the equation remain balanced. We start with americium-241. Its proton number is 94. It emits an alpha particle. So subtract 4 from 241, you get 237. Subtract 2 from 94, you get 92. If you look at your periodic table, atomic number 92 is uranium. The core trend you need to extract here in these 60 seconds is conservation. Nothing is lost, it merely transforms. Mass and charge are perfectly beautifully conserved across the equation. Section 4. Mastering half-life calculations. Let's conquer the math. This is a topic that terrifies some students, but it is actually one of the most predictable and reliable places to scoop up easy marks if you just understand the underlying mechanism. You absolutely must memorize this exact wording, as examiners frequently ask for its precise meaning to award you the definition mark. Half-life is the average time taken for half the atoms in a sample of a radioactive material to decay. Let's do Challenge 2 of our workshop. Find the flaw. I'm going to read a flawed paragraph from Sam's exam paper, and I want you to spot exactly where he loses the mark. Sam writes, "Half-life is the time it takes for a radioactive material's mass to break in half completely." Did you catch the flaw? There are actually two major ones. First, he said mass to break in half instead of half the atoms to decay. Second, he completely missed the most crucial word, average. Because radioactive decay is a totally random process, half-life is a statistical average time taken for half the nuclei in a sample to decay, or for the activity count rate to half. Never ever forget the words average or time taken. This visual graph beautifully illustrates activity dropping by half over consistent, predictable time intervals, which is exactly what half-life represents. Imagine we start at an activity of 80 becquerels on day 0. We draw a horizontal line down to 40 becquerels, which is exactly half, and see where it hits the curve. From that point on the curve, we drop a vertical line straight down to the x-axis. It hits exactly at 2 days. To check our work and prove it to the examiner, we have 40 to get 20 becquerels. The time it takes to drop from 40 to 20 should also be 2 days, landing us exactly at day 4. And it does. This confirms the half-life is perfectly consistent at 2 days. This is exactly how you prove you're working out to an examiner on a graph question. Let's move on and see how this builds into standard numerical problems. To efficiently solve a calculation like the strontium-90 problem, just follow these sequential mathematical steps. Imagine a sample starts at 480 counts per second and drops to 30 counts per second. The half-life is given as 28 years. How long did it take? Step 1. Draw a simple table. 0 half-lives equals 480. 1 half-life halves it to 240. 2 half-lives takes it down to 120. 3 half-lives to 60, and 4 half-lives gets us to 30. Step 2. We now know for a fact it took exactly 4 half-lives to reach the target count rate. Step 3. Multiply the 4 half-lives by the duration of 28 years. 4 times 28 equals 112 years. By structuring your answer exactly like this on the page, step by step, you guarantee every single working out mark available, even if you mess up the final multiplication. Moving to Section 5, Safety and Real-World Uses, let's see how this applies outside the textbook. Securing full marks also means demonstrating to the examiner that you understand how to safely handle these incredibly powerful forces. This is often where the final few points of a major question are hidden, and it relies heavily on your practical knowledge of the laboratory. Examiners expect you to easily recall these specific safety precautions that prevent dangerous ionization and cell mutations. It's time for Challenge 3, Speed Writing. You have a 30-second timer counting down right now. Your challenge is to write one perfect Peel paragraph explaining why we use photographic film dosimeter badges. Go! While you write, remember your structure. Point. Dosimeter badges monitor radiation exposure. Evidence. They contain photographic film that reacts to incoming radiation. Explanation. By keeping a precise record of the exposure dose, the badges ensure workers do not exceed safe biological limits. Link. Therefore, once a safe limit is reached, workers are transferred to protect them from dangerous cell mutations. Stop writing. If your answer looked anything like that, you just secured 3 out of 3 marks with 0 stress. Simple, practical steps like using long-handled tweezers to maintain distance and locking sources in heavy lead boxes drastically reduce radiation risks in the laboratory. Why tweezers? Because radiation intensity drops off sharply with distance, following the inverse square law. Even a few extra centimeters of distance significantly reduces the dose of radiation to the teacher's hands. Why lead? Because as we discussed earlier, lead is incredibly dense and is one of the only materials capable of reliably absorbing highly penetrating gamma radiation. See how everything connects back together? The physics explains the safety rules. Finally, Section 6, Decoding Exam Command Words. Let's crack the examiner's code. Let's decode the specific language of the examiners so you can translate your physics knowledge into top marks. You can know all the physics in the entire world, but if you do not speak the examiner's language, you will not get an A star. It's that simple. If you don't tailor your answer to these specific command words, you will lose marks even if your underlying physics is absolutely flawless. Here is the complete physics answering system. There are 3 rules that guarantee top marks. Rule 1, command word decoding. Rule 2, Peel framework application. Rule 3, time management matrix. Let's break down Rule 1 specifically, because this is exactly where Sam failed initially, and we're not going to let you make the same mistake. The absolutely crucial point is knowing the exact expectation behind every single word. When asked to define half-life, you must be incredibly precise, giving the exact textbook meaning. If asked to calculate, you must explicitly show you're working out from the given facts. No working out, no marks, even if the final number is perfectly right. State means you don't need a long, rambling explanation. Just express the answer in clear, short terms. It's a quick 1-second mark. But describe means you must give the characteristics and main features. This is where Alex usually writes way too much and wastes precious time. Only describe what is necessary to hit the points of the topic. This ties directly into Rule 3, time management. If a state question is worth 1 mark, do not spend 4 minutes writing a whole paragraph. State it and move on. If a describe question is worth 4 marks, use your PEL framework to ensure you hit 4 distinct, logical mark-scoring points. With the command words fully decoded and the core physics completely mastered, the only question left is how you'll attack your next exam arena. Are you going to be an Alex, throwing random facts at the page, hoping something sticks? A Sam, rushing and completely missing the point of the question? Or are you going to be a strategist, decoding the commands and managing your time like a pro? The tools are now in your hands. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. See you in the next one.